Okay, so with exponential growth and decay, there's a ton of different things that we can do. First of all, I want to look at, not just math actually, but I want to look at science. Cells. How cells grow. Okay, so those of you who like science, here you go. So, in this picture, there's 7 different pods of cells, and they grow in different ways. So what I want us to do, take about a minute. I want you guys to ask yourself and write down some thoughts about how these cells, or the number of cells, increase by each day. So take about a minute to yourselves, write down anything you observe. Cole, take about a minute to yourself, please. Observe what's in the picture, write down your ideas, and then we'll come back and we can talk. What do we notice with this picture? Jake, what do you notice?
That the cells like double each day.
They double each day. So it just looks like we start at 1, then we go to 2, then we go to 4. Then it looks like 8 cells, so they double after each day. Okay, good. What else do we notice? Do you notice anything else? This image. Jeremy, I'm sure that's what you were going to say. Yeah, Gage.
The blue.
These are blue. Unfortunately, I don't actually know if that affects how they grow. I'm not a big science person, whether they're blue or not. But they are. Anything else that we may notice that happens? Jake hit it pretty good. They do double each day. Which is different from like what we would know if it was just growing linearly. So like, for example, it didn't go from 1 to 2 to 3 to 4 to 5. Jake said it doubles. So from 1 to 2, and then 2 to 4, 4 to 8, which is, looks like we get to maybe 64 cells on day 6. So that's how we say that this is exponentially growing rather than just linearly growing with cells. I also want us to look at a vehicle, a car. It starts at this car, brand new car, $10,000. Okay? As the years go on, this car decreases by a certain amount of money. So again, take about a minute to yourselves, ask yourselves, write down notes about how the value of this car decreases from year to year. Maybe think about the difference in prices as it goes from year to year, or just what the prices do themselves. So we're going to take about a minute, and then we'll come back and talk. What do we notice that's happening here? What observations do we have? What's going on here? Griffin, you got something?
The older it is, the cheaper it is.
The older it is, the cheaper the car gets. So just the prices that just continue to decrease. So it's cheaper when it's older. Okay, good. Jasmine, what else?
$1,480
$1,480
a year.
a year? From 0 to 1? That looks about to be the case. What about from year 1 to year 2?
I do
Okay, well that's a good start though. You said $1,480 from year 0 to year 1. What about from year 1 to year 2? Gage?
13,007.
13,000?
Wait, no, so 1,307.
$1,307. What might that mean? From year 0 to year 1 it was about 1,500. From year 1 to year 2 it was only 1,300. What about from year 2 to year 3? Jason?
I was gonna say the prices decrease slower each year.
The price decreases each year. So from year 0 to year 1, it's up to about 1,500. Then it goes down to 1,300, then 1,100, then only 900, right? So those price differences actually decrease each year. So I'm sure by year 7, the car might only be worth $2,000. When you first buy a car, brand new off the lot, before you even put your foot on the gas pedal, it's worth about $10,000. As soon as you do, and as soon as you drive it off the lot, it bolts down immediately. Which unfortunately that sucks, that's how the economy works. As you get down to owning it for 3 years, 4 years, 5 years, it starts to look more like a piece of junk. It starts to level out at where that price range would be. Which is why this could be represented as exponential decay. As the price decreases, it starts to become more gradual. So with growth, it starts slow and shoots up, like what the cells did. With decay, starts really high, shoots down, and then it levels out at the end. So this is kind of what decay would look like. Okay. I guess that's how growth and decay would work in the world. But firstly, I want to talk about exponential growth. With growing and all that stuff, with cells, how we talked about earlier, and then how we can use it in problems. So with exponential growth, there's different functions that we use. They're almost derived from the functions that we used on Wednesday. With exponential functions, there's just different variables, but it's set up pretty similarly. So we still have that f of x notation to show that this is in fact a function. And we still have this a variable out in front of everything else, which is similar to the exponential functions we saw Wednesday. This a variable represents our initial amount. And this initial amount can be dollars, it can be people, it can be food, it can be anything that you can put a fixed number on. So anything like people, 10,000 people, that can be an initial amount. Or $14,000, that can also be an initial amount. In our exponential function equation from Wednesday, there used to be a b variable in those parentheses. That changes to 1 plus r. And then instead of to the x power, it's raised to the t power. That t in the exponent represents our time in years. And with all of the problems you'll see, everything you look at, it's always going to be represented in years. And that r, because we're talking about growth, is our growth rate. Now, whenever you see something like a rate, you usually think of it as a percentage of something. When you do some of these problems, you'll be having to change those percentages into decimals in order to use them in problems. So for example, if I have 20%, of something. How can I write 20% as a decimal? 0.20. So 0.20. For those of you who said 0.20, what did you do to change it?
Move the decimal over left.
Move the decimal left. How many places?
1.
2 places. 1, 2. That's what it would look like as a decimal. Perfect. So if you see a percentage, move it 2 places to the left. That's what it would look like as a decimal. Before we jump into a problem, I need help. On Wednesday, we talked about what these functions look like. Can somebody come up here and draw one for me? Just as general of an exponential growth function you can get. Carter, you want to give it a try?
Just general.
As general as you can be. Yep. Maybe something is like the simplest one we did the other day. Use the back end of the pen.
Come on, Carter.
Okay. We done our heads?
Yeah.
Jeremy's shaking his head.
Who's
That's
joking?
What did he draw? I heard it over here. He drew a decrease. This is exponential decay that you just drew. Because it starts off really tall and then goes gradual. So that's okay. What would exponential growth look like?
Oh.
Jake, you want to tell him what to do?
Oh. Yeah, just try like the others. Right now. Yeah, you go like the other way around. So you like flip it pretty much.
So start here.
Yeah.
That's better. Yes. So what he actually drew was both exponential growth and decay. So thank you, Carter. And Jake, I'm glad you helped him out too. Exponential growth starts small, starts really gradual, and then shoots up. Right? So this is what exponential growth would look like, just generally. Starts low and then shoots up, kind of like those cells did earlier. Okay, here's a problem. The population of Hillville, please don't ask me where Hillville is, I have no idea. Hillville is 5,000 people, okay? And that population grows at an annual rate of 15%. What do I mean by annual rate? Logan. Yearly rate, good. Grows at a yearly rate of 15%. Question is asking what the estimated population of Hillville will be in 5 years. Before I even start to do this, what is one word, the only word, in this problem that tells me that this is exponential growth? Jeremy?
Grows at an annual rate.
Grows. It grows. So we have exponential growth. We know that right away. So I can use that exponential growth function we talked about. So a 1 plus r to the t power. This happened so many times today. What is my initial amount? What can I substitute for a? Carter.
5,000.
5,000. That's our initial amount of people in this case. So I have 5,000 people. I then have 1 plus my rate. What number in my problem tells me what my rate is? Jake?
15%, so 0.5.
Perfect. Yes, 15% is my rate. Represented as a decimal, you're moving that decimal place 2 places. And then lastly, my exponent. Jasmine, what number can I put in my exponent? 5. 5 years. Time in years. Now hopefully, you have a calculator with you. You can just substitute all of that into your calculator and it will do it for you. So the 5,000 out in front, 1 plus 0.15 inside the parentheses to the 5th power.
How do you do that?
Sorry?
There's five.
How do you do that?
That's okay.
It's higher than that square.
So if you type in 5,000, do the 1 plus 0.15, above the division sign, there's a caret symbol. That just puts an exponent on top, and then you can hit 5. Jason, you said that you had like 5 decimal places afterwards?
Yeah.
That's okay. What did you get for your answer?
10,056.
10,056? Should I add any decimal places?
I had 0.78594.
So like 0.78?
Or it could just be 0.8. Yeah.
0.8.
Jasmine, you have your hand raised. What do you have in mind?
Wouldn't it be 57 at the end because you can't have like a quarter of a person?
Did everyone hear what she said?
Yeah.
You're probably missing a few limbs if you're a quarter of a person, right? You cannot have 0.78 of a person. So yes. Hit it on the head. And that is in, do not forget units, like I just did. That's in people. So, a little over 10,000 people. How do we feel about exponential growth? Pretty good so far? Do you have any questions about the function, about putting anything in, about the graph itself, before we move on to the day?